Thank you very much. Yeah, in the next few minutes, I will show you how we were able to improve the multipath interference problem in 3D time-of-flight camera with a new or optimized approach with a particular swarm optimizer. First, I will give you a short introduction to 3D time-of-flight cameras, how they work, and to the really big problem of multipath interference, and how is a way to solve that. Then I will show you what we wanted to achieve. Then I will show you what the limitations are with the previous work. This is what is available or presented already 2 years ago. And then in the end, I'm happily showing you what we were able to achieve with our new approach. So 3D time-of-flight cameras are a very nice thing. They can measure in every pixel of the imaging sensor the distance to the object. So it's not, or for example, in a LiDAR, you have to move a mirror. In a 3D time-of-flight camera, as we use it, we have an imaging sensor that measures the distance in every pixel. To do that, we send out some light that's modulated with a frequency. The light gets hit by an object, is reflected back. And what we are measuring is the phase shift, as you can see here, from the sent out light and the received light. So because that takes some time to travel, we measure this small phase shift. This gives us the distance, and this phase shift is also frequency dependent, but because we know the frequency, we can calculate the distance. What are multipath interferences? The problem is, in reality, we not only measure in one distance, we often do measure, or the light gets reflected from multiple objects back to the same pixel. So as you can see in the upper image, we have two objects. The first object 1, is a semi-transparent box or a mesh or something the light travels through. So if we now send out light, the light gets, or a part of the light gets reflected back from this object and comes back to the sensor. The rest of the light passes through this box, is reflected from the wall behind, and gets so measured by the sensor. In the end, what we are really measuring is the sum of both paths or both thickness, as you can see here on the left image. These are the phase and the amplitude in the complex space. So what we are interested in is this phase here, and this phase here from the green vectors. So the sensor does measure only the blue one because the sum of both vectors. So, and as you can see, this phase from the blue vector is completely wrong. That's not the green or not the red distance. It's somewhere in between these two objects. That's a huge problem because we, for example, in robotics, if we measure the wrong distance, the robot is directly walking into this object because it thinks it's farther away. The second problem is not only with transparent objects, it occurs also on edges because some light is reflected, for example, from my body. The rest of the light goes back to the wall, and so the sum is also somewhere in between. Or even if you have, for example, a very flat floor that's a little bit shiny, the light hits the floor, goes back to the wall and comes back, and so the floor has the wrong distance. Happily, there is a way how we can solve that. To do that, we have to measure at multiple modulation frequencies of the light. As you can see here in the simulation on the lower left, the blue one is again the measured vector. The green and the red ones are two simulated objects that's reflected from the scene. So if we increase the frequency, that you can see here that the green one and the red one are constantly or linearly increasing their phase because the time the object is always the same, but if we increase the frequency, the phase also increases. But as you can see, the sum here, the blue vector, is constantly changing and is not directly correlated to these other vectors. If we use that in theory, for example, if we have two paths here, we need to measure at two frequencies. These are what we are measure is the blue one, the Z vector. So we measure there a phase and amplitude, and what we are looking for are the amplitude, so the length of each of these vectors, and the distance or the phase of these two vectors. So we want the phase and amplitude of the vector or the distance 1, and the phase and amplitude of the distance 2. So this is just a simple equation. Because in reality, you have noise, measurement noise, and also the components of the time of flight camera are frequency dependent. You cannot only measure at two frequencies and get a result that is a good result. Instead, in our cases, we had to at least measure at 5 different frequencies to get some good results. To solve these equations with 5 measurements, there are multiple ways to do that. One way is the so-called orthogonal matching pursuit. This is also published 2 years ago, where they told this is a good way to solve the problem. As I will show later, in some cases it's a good way, and but it has also some really annoying limitations. What we wanted to do is now to use a global optimizer like a particle swarm optimizer that is able to solve the problem not iteratively as the orthogonal matching pursuit, but instead tries to solve it as in a whole and guesses the distances together. So we wanted to improve the distance accuracies of these estimated distances, and also reduce the minimum distance difference between two objects. Because if we measure two objects that are too close together, we are not able to separate them anymore, but instead we measure some middle distance. And this is very important for the reality, because a lot of objects are very close together. For example, if you have a plastic box on the ground, most of the time the ground is very close to the surface of the box. To do that, to test that, we built our test setup. On the left side, you see the time of flight camera. On the right side, you see a mesh. This is our semi-transparent layer. And behind here, the black, this is the wall for the second layer. For some measurements, we also added some stray light, some very close object that is close to the camera, but not in the line of sight of the camera. This is also a problem because of lens, non-ideality, where we have if the light gets reflected and this some lens flare, even it's not in the line of sight. So what are the limitations of the previous work? To show that, we set up a measurement with the mesh at 2 meter distance from the camera and the wall at 4 meters distance from the camera. So the difference between these two objects is 2 meters. On the left side, you see the raw image measured at only one single distance, frequency. What you can see here, we wanted to see a distance at 2 meters and at 4 meters, or if it's not possible to measure both with one frequency at least, we wanted to have, for example, a distance at 2 meters. But instead, we measure some mix of both signals at 3 meters. On the right side, you see the previously published OMP algorithm that is also not able to separate these two distances because they're too close together. Instead of some some stray light at 0 meters, the correct distance at 2 meters, and at 4 meters, we measure a mixed distance of 3 meters between the two layers. This is due because the orthogonal matching pursuit tries to solve for the for one vector or one distance at a time and iteratively then tries to solve the next vector. And because when these two vectors or measurements distances, for example, these 2 and 4 meters, are close together and have roughly the same amplitude, these are merged together and we only measure one distance. And therefore, the distance at 1 meter and the distance at 5 meters are just additional errors because the algorithm wanted to compensate for the error it did in the first place. With the new approach, with the particular swarm optimizer, we were able to solve the problem of that minimum distance difference. Here you see again on the left side the raw image with a single frequency and the wrong distance. On the right side, you see the achievement we were able to produce and separate this distance very well. You see here on top the stray light we added, and this is close to 0 because it's very close to the camera. Then we were able to separate these 2 and 4 meter objects perfectly fine. As you can see, we were also able to measure it quite accurately because here you see a slightly curved. That's because if you look at the wall from a single point, the distance in the edges are farther away than the distance in the middle. This is clearly visible here. But 2 meters distance, minimum distance difference between two objects is still very far away. So we increased our efforts to reduce this distance further. So we made up a test setup of 2 meters for the mesh and 3 meters for the wall. Therefore, we were able to separate these again with the PSO approach. And yeah, we got some really nice results here. On the left side, you see the orthogonal matching pursuit, and we were not able, or it was not able to use that. One application, for example, for this approach is also if you want to see through some objects. For example, if you want to have your camera behind a mesh to protect it or behind a window. So in this case, we set up a toy horse behind our mesh. And as you can see here in the raw image, you just see nothing. And in the right image, you see clearly here the toy horse, and we were able to see through, for example, a protective layer. In the end, we were also added to improve the optimizer. We also added a gradient-based optimizer at the end to improve the accuracy and also greatly reduce the computational time of the particular swarm optimizer approach. So in the end, what we were able to achieve was we could reduce this minimum distance difference between two objects from 2.7 meters to 0.75 meters, roughly. This is still relatively big for real-world applications, but for us, it's a huge improvement because we could reduce it by about 2 meters. What we also were able was to decrease the error of these distances a little bit. And what we couldn't improve was the standard deviation of the measurement or of this, for example, of the wall. To note, this value seems quite high because these are generated or measured at objects that are roughly 5 meters away. So if we are closer, we are much better than these 0.3 meters. Thank you for your attention.